Section 4.3 is called Greatest Common Divisors and Least Common Multiple. What we're going to take a look at today is two different quantities. I'm hoping that we'll finish the greatest common divisor part of it today, and that we'll do the least common multiples part on Wednesday. That's my plan, okay? We're going to look at first what this means. We're going to look at multiple ways of finding these quantities. There are pros and cons, just like with many of the things that you've learned in this class so far, of the different methods. And depending on the problems that you're looking at, sometimes one method is preferable to another one. And sometimes it's just, you have a personal preference and you like to do things one way or another. So to start with, let's just talk about what a greatest common divisor is. First of all, it has two names, greatest common divisor or greatest common factor. You'll hear it called either one. Your book uses the word divisor most frequently, greatest common divisor. This is the greatest whole number that divides all the numbers in a set. And I realize there's a second definition on there, but just write it in if you want to real quick, but let me talk a little bit more about greatest common divisor. Greatest common divisor is typically a small number, okay? Because it's a divisor, and a divisor means it has to divide what you started with. So with very few exceptions, the greatest common divisor is going to be smaller than the number or numbers, in this case, you were given. So a greatest common divisor is a relatively small number, right? We're going to get to least common multiple next time, and in spite of the fact that it has the word least in its description, it's a multiple, which means that it is something bigger than what you started with. So please keep in mind, this is my English for the day. It's about this much right here of how much, not that I don't know more English than this, but this is the importance of the way that this is describing this. The word greatest is an adjective, and it's modifying the word divisor. Okay? Doesn't mean it's a big number. It means it's describing the word divisor. It's the biggest divisor. Relatively prime. We have encountered the word relatively prime or phrase relatively prime before because I just can't not say it when we were describing the divisibility rules for 6. Relatively prime is simply two numbers or more that have no factors in common except for 1. Numbers always have the factor 1 in common. So we had this happen when we were talking about the divisibility rule for 6. The reason the divisibility for 6 rule worked is because 6 could be broken down into two numbers that had nothing in common in terms of their factors except 1, 2, and 3. And we encountered several others, or we described several others that we could do that with. For example, we talked about the number 24. There are ways to break down 24 that are not into relatively prime pairs, right? Like 12 and 2. 12 and 2 have something in common. 4 and 6. 4 and 6 have something in common. But 3 and 8 don't. So we would say that 3 and 8 are relatively prime. That doesn't mean they're prime. It just means that relative to one another, they don't have any factors in common but 1. Okay, so we're going to encounter that phrase a couple of times in our lesson. All right, so we're going to jump right in with greatest common divisor methods. So these are methods for finding GCDs. The first one is intersection of sets method. This method says that we're going to list all the divisors of our numbers out. So we're going to list them. You can list them in pairs if you'd like. You can list them in, from smallest to largest if you'd like. Doesn't matter. You're just going to make a list of all the divisors of your numbers. And we're not talking prime. We mean divisors, like all the divisors of the number. Okay? And then whichever number is the largest and in both lists, that's your greatest common divisor. It's the largest number in both lists. So we're going to start with some numbers that are pretty small to do this with, 12 and 15. So I'm going to write down the divisors of 12. So I don't have this in my notes this way, but I'm going to put these in pairs. So if I did pairs of these, I'd have 1 and 12. What's the next smallest number besides 1 that divides 12? 2, and it'd be 2 and 6. What's the next smallest number that divides 12? 3, and then we get 3 and 4, and then we're done because there is no more space between 3 and 4 for whole numbers, right? That would work. Let's do the same thing with 15. So we start with 1 and 15. What's the next smallest number that divides 15? 3, and it'd be 3 and 5. Okay? And then again, there's no space between 3 and 5 except for the number 4, and 4 doesn't divide 15, so we're done. So we're looking among these two lists or between these two lists, and we're saying what is the biggest number that's in common to both lists, and the answer is 3. Right here. It's in both lists, and it's the biggest one. So that's my greatest common divisor. Notice, it's 3. It's smaller than 12 and 15. Also notice it does divide 12 and it does divide 15. So at least we know for sure it is a divisor. It does work. And when we've written out our list, we notice that it's the largest one. Okay? When might this be an effective way to do this? Can you give me an example of when you might decide this would be a good way to do it? Let me change the question a little bit. Why might these two numbers not be useful in this particular method I just did before? They're awfully large, right? When I did 12 and 15, it was nice to do these lists because they're small. So this idea of writing out a list of things when something is a small number is an effective way and an efficient way to do it. But once the numbers get quite large, especially larger than we mentally use, that makes it much more difficult. Does that make sense? Okay. All right, let's do another method then. Second method. This one's going to kind of beckon you back into what you were doing in the last section. This is called the prime factorization method. Okay, so let me pause while you fill in the holes of your notes, and then we'll talk through them. The blanks that I choose to leave for you to fill in aren't just randomly decided. It's not like I said, I'm going to take out this letter or this word, whatever. I usually leave the blanks in places where that's the key point. It's the key idea to the whole thing. So like the first one says construct, and the blank said prime factorization, right? That's the important part, is that we're going to do prime factorization on step 1. Step 2, the word that you filled in, I think was the word common, right? It's the idea that things are common to what's going on. So keep that in mind as you're filling in those gaps, is that they're on purpose left for you to fill in, right? So let's go through this. Step 1 says that we're going to construct the prime factorization for each number. That's exactly what you guys did in the last section. You did factor trees, or you did this division sort of a step-by-step, it looks like a ladder going down, where you wrote out all the prime factors, and then in the end you wrote things like 2 squared times 3 to the 5th times 5, something like that. Okay? So this is what step 1 is. Step 1 is to do that. It's to do what you did in section 4.2. Step 2 says to look at those factorizations and find the prime numbers that are in both of the numbers that you're working with, or all 3 of them, or all 4 of them, however many numbers you're trying to find them for. What number is common to all of your numbers? What prime numbers? And you're going to use that number. Okay, that's step 2. Step 3 says those factors that you just wrote down, those prime numbers, you're going to give them exponents. The exponent you're going to give them is the smallest exponent from the numbers you started with. So if one number has an exponent of 2 and another number has an exponent of 4, you're going to use the 2. Okay? So you're going to use the smallest exponent. And then step 4 is that you're going to multiply that back out. Whatever you got in the prime factored form, you're going to multiply it out, and that's going to be your greatest common divisor. Okay? So we're going to do an example, and they are larger numbers. That's totally cool, though. We can do it. We're going to deal with the numbers 400 and 360. Okay, and I know that you guys are good with factor trees and you probably like them a lot, so I'm going to do the other method today when I'm working, because that's the one that you're least comfortable with, and I want you to get a little more comfortable with it. In particular, what you're doing is you're dividing by the smallest prime number that divides each number. So 400 divides by 2, and you get 200. 200 divides by 2, and you get 100. And 100 divides by 2. Are we almost sounding like a broken record? Just almost. And we get 50. 50 divides by 2, and we get 25, which does not divide by 2. But it does divide by 5. So we get 5s at the end. Now before we move on to the next number, let's actually write out what this is then. This is a 2 raised to what power? 4 times 5 to the second. Very good. This is the prime factorization for the number 400. Our second number is the number 360. Also even, so it also divides by 2 to give me 180, which divides by 2 to give me 90, which divides by 2 to give me 45. Now 45 no longer divides by 2, and you might be tempted to jump ahead and do the 5s, and if you did, I'm not going to like freak out on you or anything. It'd be okay. But technically what you're supposed to do at this point is the smallest prime number, and there is a smaller prime number than 5 that divides this, and that would be the number 3. And that would give me a 15 here. It divides by 3 again to give me 5. So what is the prime factorization for this one? I have 2 to the what? Third. And then I have 3 squared. And then I have 5. This is step 1. Step 1 is getting this prime numbers with the correct powers at the bottom. That's step 1. Step 2 says, looking at those lists of prime numbers with their powers now, find the prime numbers that they have in common. So what prime numbers do they have in common? A 2 and a 5. So as I'm creating my greatest common divisor here, I know it is going to have a 2 and it's going to have a 5. Some people forget this step and they just say, okay, then it's 10 and I'm done. Now 10 would be a common divisor for this. That actually would be a correct answer for what's a common divisor, but it wouldn't necessarily be the greatest common divisor. Step 3 tells me I need to look at the exponents. What is the smallest exponent on the 2's? 3. So that's the exponent that I need on my 2 as well. And then I need to look at the 5's. What's the smallest exponent on the 5's? It's a 1. You don't actually see it here, but this is a 1, right? So this 5 has a 1 exponent. Either write it or don't. What is 2 cubed? 8. And then I have 8 times 5, which would give me 40. So this is step 3, writing this out. Step 4 is actually multiplying this out together. And that would give me the number 40. So the greatest common divisor is the number 40. It's not a bad idea to make sure that it really actually is a divisor. Like if you take 400, will 400 divide by 40? Yeah. And then will 360 divide by 40? Yes. So at least I know I've got a divisor. It may be that I missed something along the way with the greatest common part of it, but I do know at least this is a common divisor. So I got kind of part of it that I can check real quick. All right, so this is the second method we did. Works really, really well for most numbers in general, but especially if you've got something that's large, lots of factors in common, things like that. Let's do another one. The next one is called division by primes. This is actually probably my favorite one. I like this one quite a lot. I like the last one okay too, but this one I like a lot. So what do we do? Well, you fill in the blanks first, and I'll be quiet. All right, looks like we're getting close. All right, so the first thing we do is whatever the numbers are that we're doing this with, trying to find the GCD for, we put them beside each other. I mean, there's some space between them, but we're going to kind of put them in a row, horizontal row, okay? And then we're going to look for a number that's a prime number that divides both of them. Now, technically, does the number have to be prime? And the answer is really like not technically, except that the title is division by primes, which means that technically we probably should be dividing by primes to fit the title for the description. But let's say, for instance, that you notice, hey, they're both divisible by 10. Could you divide by 10 and then end up getting the right answer at the end? Yeah, you could. So this is sort of a technicality for this. But you look for a number that divides both or all 3 or all 4 of the numbers you're working with. And then you actually take whatever the quotient are, that is the result, and you look again. And you say, okay, well, are there any other numbers that divide the answer that I just got? And you keep doing that. You repeat that step until whatever you're left with at the bottom are numbers that are relatively prime. They don't have anything else that divides them except the number 1. Okay? So let's actually do this. And then whatever the result is from what the numbers are you divided, the product of that's your answer. So we're going to start with 410. And 360. So here's my row. I've written them right next to each other. And we're going to do a division that looks a lot like the divisions I was doing just a moment ago, but it's going to go towards both of these numbers and not just one number. Okay, so technically, you should be looking for a prime number that divides both of them. What's a prime number you know that divides both of these? 2. Smallest one, 2. All right, so what's 410 divided by 2? 205, great. And what is 360 divided by 2? 180. We just did that one a minute ago, right? All right, 205 and 180 are not both divisible by 2 now, right? So we're not going to divide by 2 again. Are they divisible both by 3? No, 205 doesn't work. The next prime would be 5. Are they both divisible by 5? Yes, they are. So now we're going to divide by 5. So what's 205 divided by 5? 41. And what's 180 divided by 5? 36. All right, 41 and 36. Do they divide by anything? Both of them. Well, we know we don't have to test the numbers that I already tested, right? Don't have to test 2 or 3 or 5. I already looked at those. I guess technically we could test 5 again, but we see that 5 doesn't work. 7? No. And in fact, I've gotten a number that's quite too large because remember I have this ability that says I can square root the numbers to tell me how far I need to try. So what's the square root of 36? 6. So I don't need to go above the number 6, right? So these two numbers, 41 and 36, do not have anything in common. They are relatively prime. So what's the answer to the question? Well, the answer to the question is the product of the numbers on the outside that I multiplied by. The GCD is simply 2 times 5, which is 10. The reason I like this method is because while this is very organized and clean and neat and tidy and all that good stuff, at least as long as I make it that way, you know, it can be that way, you end up doing a lot of work you didn't really need. I don't really need prime factorizations of both of my numbers to get the prime numbers that are in both of them. That's exactly what this one does. It's the least amount of work to actually find the answer. All I had to do was look at the numbers that were working for both numbers at the same time, and that's pretty efficient. One more method, and then we'll be done for today. The last method is called the Euclidean Algorithm. It's a little bit funny. It doesn't look like the other methods at all. So jot down the answers in your blanks for this one. All right, so you're given two numbers. Step number one just says you're going to divide the larger number divided by the smaller number. Okay? And then what you get is the remainder, so the number on the bottom, and what you divided by, you're going to take those two numbers and do the same thing again. You're going to divide larger number by smaller number. And you're going to keep doing this until you get a remainder of 0. Okay? So let me show you it, because it's actually very efficient as well. It's very clean. It's just a little bit hidden as to what it's doing and how. It's not quite as obvious as the others. So if I divide 76 into 126, it goes in one time, and I subtract 72. I didn't say 76, I meant 72. What is 126 minus 72? 54. As long as the number is smaller than the number I divided by, then that's an acceptable remainder, right? I take these two numbers and I divide them. Bigger number divided by smaller number. How many times will 54 go into 72? One time. And then I subtract my 54. What's 72 minus 54? That is 18. So again, I take the value I divided by, and I take the remainder. Remainder's on the outside because it's smaller. The value I divided by, the divisor, is on the inside. How many times will 18 go into 54? 3. What's 3 times 18? It's actually 54, right? So I get a remainder here of 0. The fact that I got r equals 0 here tells me to stop. So you don't have to actually write that in when you're working your problem, but I want you to have it in your notes so you remember that's the stopping point. Once I get remainder of 0, the answer is I'm ready to stop. What's the answer then? It's the last number I divided by. That's the GCD. So my GCD here is 18. And again, I didn't emphasize it on the last one, but again, one way to check and make sure it's actually a divisor is to check. 72, does it divide by 18? 126, does it divide by 18? So at least you can check to make sure that it's actually a divisor.